In this video, I'd like to talk about what is known as the Pythagorean Theorem. So, Pythagoras, the person that this theorem is named after, was a Greek mathematician from about 2,500 years ago. And a theorem is something in math that has been proven true or can be proven. And specifically, this Pythagorean theorem relates to right triangles. And it describes the relationship between the sides of a right triangle. So let me write that down, that the Pythagorean theorem describes the relationship between the sides of a right triangle. So like I said, this theorem, this proven statement, describes how the sides in a right triangle relate to each other. And it's important, the triangle has to be a right triangle. And essentially, what that means is that the triangle must contain a right angle. So let's look at some general right triangle and we can look at what this relationship actually is. So let's say we just have some random right triangle and we can say the side lengths are just A, B, and C. And I do want to denote that C, this is the long side of the right triangle. It's the side opposite the right angle, and that has a specific word. We call this the hypotenuse of the right triangle. So the long side is always known as the hypotenuse, and this theorem mathematically can be written as the sum of the two sides or the two legs of the right triangle that are not the hypotenuse, and we're going to square them. And this is equal to the hypotenuse squared. So a squared plus b squared is equal to c squared. So we square the two legs of the triangle and then add them together, and that's always equal to the hypotenuse squared in these right triangles. So this is the Pythagorean theorem. And if I make a little bit of room, we can also look at this theorem in a different way. In fact, we can look at it the way that the Greek mathematicians who came up with this theorem or discovered it, depending how you want to look at it, how they interpreted this theorem. So we can again have some right triangle, and I'll need to make this one a little bit smaller just so that we have enough room. And we can again call the side lengths A, B, and C. So I'll use the same lettering. So this is A. Let me get off of my line tool. So this is A, this is B, and this is C. So the way the Greeks interpreted this theorem is not in this algebraic formula type of sense. They thought of it more that if you created a square based off the side length of A, so if we had a square built off of A, and we had a square built off the side length of B, that if you added the areas of these squares, that they would be equal to the square built off of side C. So again, the way that the Greeks interpreted this is that the area of the square built on side A plus the area of the square built on side B, if you add those areas together, you get the area of the square on side C. So either way you want to interpret that will work, but for these example problems, we're mainly going to use this theorem to figure out missing side lengths. So if we have some right triangle and we're missing one of the side lengths, we can use the Pythagorean theorem to find that missing length. So we basically will just need to match up these numbers and the missing side to A, B, and C in our theorem. So let's do that for this problem. And with the two legs of the triangle, the ones that are next to the right angle, it doesn't matter which one you call A and which one you call B. So we can call this A and we can call this B. And if we switch that, that would be perfectly fine as well. The important part to remember with this theorem is that the side that is opposite the right angle, this has to be called C. So the hypotenuse is always C in this theorem. So we can just plug these into our formula now and then try to solve this for c. So we have that 5 squared, that's a, so a squared is 5 squared, plus b squared, which is 12 squared, is equal to, well, x is equal to c, so we have x squared here. And 5 squared, that's just 5 times 5, that is 25. 12 squared, that is 12 times 12, which is 144. And this is equal to x squared. So let's continue over here. 25 plus 144 would be 169. And at this point in the equation, we need to solve this for x. And right now, x is squared. So we want to think which operation essentially will cancel out squaring. And the inverse of squaring is taking a square root. So if we take a square root of each side of this equation, we can cancel out this square and just get x. Now, usually when you do this, you have to write plus or minus for the side with the square root to indicate that there are actually two answers that would make this true. In fact, the square root of 169, what number multiplied by itself, is simply 13. So 13 multiplied by 13 is 169. But if we have negative 13 and we square that, we also get 169 because negative times a negative makes a positive. Now I mentioned this is what we would usually do, but because we're dealing with physical side lengths here, we don't need to concern ourselves with the negative of this. So we can ignore that since we're dealing with physical side lengths. But if this was just some normal algebraic problem not related to a physical side length, then we would need to put plus or minus to account for the fact that there are two numbers which, when multiplied by themselves, give us 169. So what we found here is that our missing side length is simply 13. So the sides of this triangle are 5, 12, and 13. So that would be our final answer there.